Okay, so this might be familiar to some in the room, but let's just quickly review what SVE is. So the SVE instruction set is a class of instructions known as single instruction multiple data. So these are instructions that encode a single operation, which then is applied to multiple independent lanes of a very large vector register. So as such, SVE builds on the sort of technology that you've seen with things like Neon and Advanced SIMD, but with much wider vectors. Hence, you can do more operations at a time. In fact, the vector length of SVE is dependent on the actual processor that you run on it. The scalable part of SVE refers to the fact that you can write portable code that will run on any SVE implementation regardless of the actual vector length that is implemented in the processor. This means that your mobile system on a chip might implement the minimum vector length, but if you run the same code on a high-performance computer with super wide vectors, it will still run, but you'll get the performance boost automatically of being able to do more operations at a time. Of course, none of this is actually useful unless your code is vectorizable. This is something that generally tends to be done by the compiler. You hope it should be done by the compiler, although you might find some people will write assembly by hand. So let's look at an example of what vectorized code looks like. This is the classic C string copy. I'm hoping everyone's reasonably familiar with what's going on here. We've got 2 pointers, a destination and a source. We go through the source, copying it to the destination until we hit our termination. Now, everyone can probably write a bit of assembler that does this naively by loading a byte at a time into a register, checking, writing it out. But let's look at how this code looks in SVE. So this is an example of a vectorized string copy. Now don't worry about the details, I'm going to go through each bit in detail, so you don't need to take it all in now. Let's go through it a chunk at a time. So the first thing to understand about SVE is the use of these things called predicate registers. A predicate register is a bit field which controls which elements in the vector are going to be operated on by the SVE instruction. So here, we're setting the P2 register, predicate 2 register, all true. So what this means is any operation where we use the P2 predicate, we want to use every available lane, however many that might be, of the vector register. So, the first step of our string copy is we need to load a chunk of the source string into one of the vector registers. As P2, as we said before, is all true, we will load as many values as we can into the vector register Z0. On the default implementation, the minimum size of the SVE vector is, I think, 16 bytes, but it could be we're running with a 2048-bit vector register and we'll copy 256 bytes in one time into the vector register. Now, reading all this data at once does actually present a couple of interesting problems. One of which is if your string happens to be at the end of a page, you could be in a situation, although your string ends before the page, you've just read a whole bunch of extra data and possibly faulted. And SVE introduces this mechanism called the first fold register that allows you to read the data into the vector register and know how many of those loads were valid. So that's all that this RDFR instruction does here. It sets a new predicate register to be the total number of valid bytes that we've just read. So, the next thing we need to do is we need to detect our termination conditions. So we need to test for the null byte. So the compare instruction, much like you would do with a normal scalar instruction, we are comparing to the immediate value of 0, but we're going to compare it across all the lanes of the vector register. And in this case, we're going to compare it for all the values that we've loaded in, and it will set another predicate register to show all the lanes which have been set to 0. You'll see why this is important in a moment. But if any of the vectors have matched our condition, we'll set the appropriate flags and then we will exit this loop here. So we've tested for our termination condition, and if we've reached it, we'll just fall through. We've done our string copy. Of course, we're not quite done yet. We still need to store the result back into memory. So there's two parts to this. This is the actual store. We just store the entire contents of the Z register to X0. But we don't actually want to store everything. We want to store everything up until the first 0 that we detected, because we don't want to overwrite anything that might be after that. And that's what this break after instruction is doing. All it's saying is, for the first place that we saw a 0, set our predicate register to include all those lanes, but nothing after that. So now we safely store our remaining bytes. And finally, there's only one thing we need to do before we go around again. We need to increment our index register. So we set our index register at the top to 0, and we're using it to index into the source and destination strings. Again, the inc instruction looks at the predicate register and increments it by the number of elements that have been selected. So this piece of code has absolutely no knowledge of how big the vector register is. It will run on any implementation and automatically copy the string as much as it can in each iteration. So on a small processor doing lots of iterations, on a big one, it might just go through once. Okay, so why do we want to implement SVE in QEMU? Well, a number of reasons. For starters, we want to give developers early access to SVE. It's going to be some time before there's silicon available with SVE enabled, but the sooner people can start writing the software and testing it, the better. QEMU is obviously an open source solution, so if you're a FLOSS developer, generally people tend to prefer running a fully open stack, so there are benefits to having it in QEMU for that. Also, for academics and research institutions, they might not have access to the proprietary models, or the restrictions on their use might prohibit them from easily disseminating their work. Another reason, QEMU is faster than the model. Certainly if you're using Linux user emulation, because you don't have the overhead of emulating a full system with an MMU and everything, you can actually run code quite quickly. But even if you have to do full system emulation, QEMU also has a multi-threaded TCG now, so it can use multiple cores on your processor for the emulation, again, faster than the model. And implementing SVE is good for QEMU. These are interesting instructions to implement, and it pushes us to keep improving the core code generation capabilities of QEMU.
And it's good for testing out different vector widths, so you can make sure the code is going to be portable and nicely work later.
Yes, yeah. I mean, what we will do in QEMU is we'll implement the maximum architectural vector length, but of course we will allow you to set the system registers to limit it. So let's have a quick look at QEMU's, how QEMU does its instruction emulation. So the tiny code generator is a just-in-time recompilation engine. Basically, it operates on a basic block of instructions at a time. It decomposes them into TCG ops, which is QEMU's internal representation, much like a compiler. Once it's run through the basic block, it will run a basic optimization phase. So we do things like remove dead code or propagate constants, that sort of thing. And then we go through the remaining TCG ops, and for each TCG op we have a decision to make. We either generate some host instructions, or we call a helper function. So for most integer operations, logic operations, flow control, that sort of thing, we generate host instructions. We call helper functions for anything that we consider complex. So examples of complex instructions include system instructions that access system registers, or if you, for example, are manipulating TLB entries. We also tend to use helper functions for exception generation. But importantly for our case, all floating point operations tend to be implemented in the helper functions. That's for both scalar and vector, and I'll talk a bit more about that later. So, let's go through some of the challenges we need to address. There are prerequisite features. there's the use of a floating point library called softfloat, which we use quite heavily in QEMU. The efficiency of our code generation, and then finally I'll talk about some of the diagnostics and how we're going to approach testing. So, firstly, there are a number of prerequisites. Although SVE is an optional extension, it does mandate a base requirement of ARMv8.2. So especially, there's a whole chunk of half-precision floating point, which was added in 8.2. And there were also a couple of additional advanced SIMD instructions added in the 8.1 spec. Finally, it also mandates we need to support the complex numbers available in ARMv8.3. So to be properly spec compliant, we need to implement these instructions first. Now, let's have a look at our use of softload. So the first question you might ask is why? Indeed, pretty much all of the backends supported by QEMU already have extensive floating point support in hardware. But it turns out it's actually very hard to map the floating point behavior of one instruction set to another, even if the hardware is both bits of hardware are nominally IEEE compliant. And that's because there's enough gaps in interpretation in the spec around things like how you deal with rounding and how you deal with exceptions that you run into problems. So a long time ago, QEMU decided to do all its floating point with the softload library. So the current QEMU code is based on softload 2A. It's stuck at 2A due to a licensing compatibility that was introduced later in the series. But also, QEMU has made quite a lot of heavy modifications to that library for its own purposes. Unfortunately, because this library is quite old, we're missing out on some of the later features. So there is no support for half precision in the library as it stands, and some of the later IEEE features, the extended rounding modes, are not done there. And also, the library is no longer being developed at this release. So we need to look at options of how we're going to go forward. So one is to migrate to the softload 3 series. Handley, this is in active development and has a whole bunch of additional features, including half precision and some of the support for newer IEEE features. Unfortunately, it's a complete rewrite, so it's not a simple case of applying the changes from softload 3 on the top of our existing code. We could look at migrating to another library. There's a couple about, but one, for example, I've looked at is the GNU multi-precision floating point with correct rounding library. Unfortunately, this seems to be more designed for people doing numerical analysis, so it's not really set up for the sort of use we're going to use for instruction emulation. So that leaves us with the last option, backport or re-implement the features that we need on our existing 2A code base. And that looks like the option that we're going to go with at the moment. Unfortunately, although the softload authors are open to us providing patches and taking changes from the community, they're not really set up for it. There's one guy who's the principal developer and he looks at it once in a blue moon, so it's not really suitable for us to base our work on. Right, let's look at QEMU's code generation. So, as we've just seen, all the floating point operations are done with helpers, because we need to use softload to do the calculations. Although there is an option for integer stuff to be done in generated code, generally what we do is we break down a vector into its multiple elements and call a helper to process each element in turn. There is a cost to this, however, because every time you call a helper, you need to create a C stack frame, jump into the C code, return from the C code, and store the results back. And this is one of the reasons why QEMU is quite slow when you're doing anything that's particularly floating point heavy. You'll notice there is a difference between booting a kernel and, say, for example, running FFmpeg. The QEMU TCG is currently limited to it just understands the ideas of 32-bit and 64-bit operations and registers. We've had previous attempts at expanding, supporting SIMD instructions in the TCG, but it tended to get quite messy because you need to add a set of operations for every single size of SIMD register that you need to deal with. So the latest approach we're having, the latest attempt at this, is we've actually come up with a way of having a size-agnostic way of representing vectors. So we can treat a vector as an arbitrary sized vector from a code generation point of view, and then call the helper once. So you've got 4 lanes of 32 bits, or you've got 16 lanes of 32 bits. It'll be the same code, and without having to complicate the TCG more. This does leave us with scope also for generating code for some of the simpler operations as well. Let's have a quick talk about diagnostics. So, although most users of QEMU don't tend to look too much into the details of what QEMU is doing, it is useful for more advanced users and certainly for developers to be able to see both the guest code that we're running and the generated code that we've generated. On the guest side, things are fairly good. We use a library called libvixel, which I think came from ARM and is now a Linaro-hosted project. But on the host disassembler side, it's not so good. The host disassembler is currently based on an old forked version of Bennée tools from before they made their GPL v3 license change. And as a result, it doesn't recognize a whole slew of the modern SIMD instructions that you'd expect. So we're currently looking at the Capstone engine, which is a liberally licensed BSD library for doing our disassembly. I'd like to take a little bit of time to talk about testing. So when we did the original ARMv8 work, we used a tool called RISU, which stands for Random Instructions in User Space. It's very helpful. It works by generating random instruction patterns, and you record a trace on a reference piece of hardware, look at what changes have been made to the registers, and then you can compare that with your run under QEMU. And it was very helpful during our ARMv8 work. It caught an awful lot of corner cases which you wouldn't have necessarily come across just by manually testing. To do that, however, we are going to need to make some changes to QEMU's Linux user support. Because SVE signal frames can be so large, they're not generated automatically for all signals. There is now an optional extension to the signal frame, and we need some support in both QEMU's Linux user and in RISU to handle that.
So can you give more details of the first one, RISU? That is a component in QEMU?
It's not a component, it's a tool that we use to test QEMU.
Outside the...
Yeah, outside QEMU. But so the RISU binary is a Linux user binary that you give it a blob of data, which is an instruction stream, and then it runs each instruction, and then after each instruction saves the state of the register file. So you can compare one run under QEMU against a run you've done on some real hardware or a verified model. There is if you look on the KVM forum website, I did a talk on RISU a couple of years ago, so if you search, you should be able to find it. So, just to summarise our status, currently in progress, we're backporting or re-implementing floating point, half-precision floating point for our soft float library. The variable length vectors in TCG operations has been posted on the list. I think it's up to version 3 now. As part of this, we've also been reviewing the kernel support, although it doesn't directly affect us, because the kernel is introducing a new API for accessing the SVE registers. We thought we'd better chip in our 2 pence on the design of the API. There's work currently going on the 8.1 advanced SIMD instructions, and again, the Capstone disassembler that I mentioned, there are posts on the lists. So that leaves us a fairly hefty to-do list to get through. Obviously, we'd like to get RISU support fairly quickly because we need that for testing out all the rest of the instructions. And we've got to actually implement all the half-precision floating point operations for 8.2, the complex numbers, and then we've broken down the SV work into a number of separate silos. So handling the predicate instructions, handling memory faults, there are just minor changes with the way SVE handles memory because you can deal with these faults that occur halfway through a wide load. Then the load and stores, and then the calculations. Hopefully, most of the calculation instructions will be able to reuse the existing neon helpers under our new variable length framework. And then finally, I've already mentioned the Linux user support for the SVE stack frame. For system emulation, there are a few additional system registers that allow you to limit access to the vector registers from user space and between user space and kernel. And with that, I think we come to any questions. There should be a microphone there if anyone wants to use it.
Have you looked into LLVM-based disassembler?
No.
Capstone does. It's built off of that.
Ah, okay, because that will give you 8.3 instructions all the way to 8.3.
Yeah, so on the other side, it shouldn't, well, I should have mentioned our current usage of libvixel is a little out of date, so we need to update it, but I was hoping that libvixel would be fully up to date for the latest instructions, but there is certainly an argument with bringing Capstone in. Why don't we just use Capstone for everything? Any more?
So did you consider how GDB stuff.c in kernel is affected by SVE stuff?
There shouldn't be any major changes. There's the representation of the SVE registers, but the GDB already has a way of declaring them. So if it can't declare a super wide register, then we might need to do some work there. Yeah, there's a microphone if you everyone here.
I can just speak up. So did you run the QEMU on x86 host, right?
That's the most common way to run QEMU, but it's got code generation backends for ARM,
PowerPC,
PowerPC,
Z-Series, Spark, and MIPS.
Yeah. But most people tend to run it with an x86 backend, so that's by far the most tested backend. John?
Is, I know there's work going on extending ELF to add various attributes around the SVE requirements for user space API. Is anyone working on a bin format MIST wrapper? So I could, be on an ARM system that doesn't support SVE and just run QEMU user in that case?
Good question.
If the host wrapper can distinguish the bits that the host can't.
Yeah, because they're adding allegedly.
They're adding a flag to.
There's going to be an extension of the ELF header allegedly.
There's no reason why you couldn't register that to pop it into the.
I'm just thinking out loud, so someone could say, "Oh, that sounds interesting."
I feel like it would be a bit of a nasty surprise if you're on your native ARM system and you run something that's SVE and it will suddenly run like
not for
that.
production, goodness. But it might be fun to, because I think a lot of people want to run on ARM servers, even for development purposes.
Don't ARM also have their own solution that traps access to unimplemented instructions and emulates them for you?
Yes, I think so.
That's the current way of doing it.
Yeah.
But in their models, that's not.
No, it's a separate tool.
Yeah.
Yeah.
That's a tool that runs native.
So, which is what you want, right? You want to run stuff that's your host supports at full speed, and then you just set that stuff you haven't got. So that's a much better bet than using QEMU for the whole lot.
That's not open though, right?
No.
So I'm just saying.
Yeah.
Can you expand a bit on how you're going to test this? Because you said the execution thing was, well, we run this on hardware and dump the registers, and we run this on QEMU and dump the registers, but well, you have no hardware. So you're going to rely on what? Open models or closed models, and which version of the models?
So yeah, at the moment our reference platform will be the model, so it'll be the ARM model.
Foundation model.
Yeah, foundation model.
Right.
So yeah, you're right. If it gets it wrong, we'll get it wrong too.
Okay. It's just making sure that the expectations are set.
Yeah.
It'll be ARM's fault.
Yeah, at the back.
Is there any real TCG test suite in QEMU at this moment? Because I don't remember one. Or is it you're doing?
Sorry, I didn't hear that.
Is there any TCG test suite in QEMU, or you are doing that on your own?
So, certainly from Lenore's point of view, we have some tests in Lava that check the instruction emulation that we've added hasn't regressed. But none of this is built into QEMU's inbuilt check system. It's been a long-running pain point that we've known about, and we have some plans to use the cross-compiling support that is now built into the build system to actually build the tests for the foreign architecture so we can then run them, but that's not being done yet. Okay, any more questions? Well, thank you very much then.